First of all, I like to join the speakers thanking the organizers. Non-locality is one of the most surprising or counter-classical features and well known about quantum theory. That means correlations obtained from quantum measurements cannot be explained by local realist model. This is a standard Bell test scenario where source, bipartite source coming from source, and one goes to Alice and an observer, and other goes to Bob and another observer. They measure projectively on their sides, and they have they can choose from two measurements, and the measurement outcome are two, that is dichotomic observer, and correlation between Alice and Bob's measurement given by the joint probability from the joint probability. With this measurement statistics, local realist bound of the CHS expression is 2, whether with this choice of projective measurements, in quantum theory, this CHS expression can go to 2 root 2, that is Cyrilson bound. Another feature of quantum theory is the monogamy nature of quantum non-local correlation. That means for a tripartite state, if Alice and Bob share non-local correlation, then Alice and Bob Alice and Bob share quantum non-local correlation, then Bob and Charlie and Alice cannot share, which is clear from this expression. If this is greater than 4, this cannot be greater than 4. It is important to note that this monogamy restriction is only holds when all correlations coming from the measurement by the observers are no signaling. If this no signaling principle is dropped, then monogamy of non-local correlation cannot be held anymore. In this scenario, non-local correlation cannot be shared by more than 2 parties. So let us consider this scenario when Alice measures projectively and there is Bob 1, means if Bob 1 also measure projectively, then there is no possibility to get non-local correlation by measurement statistics obtained from Alice and Bob 2. As Bob 1 measures on his subsystem and he delivers his subsystem to Bob 2, and Bob 2 measures on his subsystem and he delivered to another observer. There is a series of observers and they measuring on their subsystem independent of the previous observer. In that scenario, Bob 1 can signal Bob 2. That is, no signaling principle does not hold for these 2 parties. So one can expect sharing of non-locality by these observers, Alice and Bob 1, Alice and Bob 2, and Alice and Bob 3, and so on. Now the question is, how many Bob can share non-local correlation with single Alice who measure sharply, and here he measures weakly and the final Bob measures sharply. If there is more observer, all the previous observer measures weakly and the final observer measures sharply. In this paper by Silva, Gisin, Elena and Popescu, they shown by intermediate weak measurement there is no double violation of Bell-CHS inequality. Means Alice can share at most with 2 observers non-local correlation, but not more than say 2 observers on the other side. Now it is left open, it was left open to prove this analytically. They have shown this result from numerical evidences and it was left in this paper to prove this analytically. Now in next few slides I want to discuss about weak measurement, which is well known here who attend school and conference. In standard von Neumann measurement, projective measurement, there is coupling between system and pointer observer, which is called ancilla or probe. And in the limit of strong measurement, pointer state can be perfectly distinguished that they are described by Dirac delta function. In another limit of weak measurement, that is extremely weak, pointer state covers all the spectrum of the eigenvalues. That means one cannot distinguish the pointer states corresponding to different eigenvalues, and the initial system state does not perturb at all, and no information gain as well. It is a realistic, typical realistic standard luck scenario. Here the wave packet corresponding to up and down spin, there is a overlapping zone. In ideal, in strong measurement, there is this overlap is 0, but in realistic case, there will be always a non-zero overlap. For two-level system, it is a generic pure two-level pure state. This intermediate weak measurement characterized by two parameters. One is called F, which gives the overlap between the two pointer states, and G is called precision of the measurement. F and G, these two parameters characterize this weak measurement. And it is the optimal pointer state. They derive the optimal pointer state which obeys this relation between F and G. That means for a given F, means that a given disturbance, how much one can gain more, how much one can gain information. Optimal pointer state is the pointer for a given disturbance one can gain maximum information. Now, in this paper, Archon Majumdar and Dipankar Home as the co-author and my supervisor as well, we show analytically this by casting the weak measurement in terms of POVM. Now, what is POVM? It is the most generalized quantum measurement. Any quantum measurement can be described by positive operator valued measure. That means POVM element are positive operator, sum to identity, and there is a trace functional rule which gives probability, and the states transformation, that is post measurement state, is given by Luder transformation rule up to unitary freedom. In any measurement scheme, there are stages like preparation, measurement, and end is registration or recording of the outcome. And this is defined, any general measurement scheme is defined by the quadruple. This is Hilbert space of apparatus, initial state of apparatus, unitary coupling between system and apparatus, and the pointer observable. It is desired that probability measurement statistics obtained from the recording data can capture the observable measurement statistics of the observable. This after unitary coupling between system and ancilla, there is measurement on the probe, and after tracing out ancilla, one can get the reduced state of the initial state of the subsystem. That is state transformer. I means state transformer. This is a probability reproducibility condition which ensures measurement statistics from device is equal to the measurement statistics of the observable measured on the subsystem. Now, what is the appropriate POVM of the weak measurement discussed earlier? To model the weak measurement in terms of POVM, we consider one parameter answer POVM, which is introduced by Paul Bush in 1986. Here lambda is the sharpness parameter. For lambda equal to 0, this is projector, and for lambda can lie in between 0 and 1. So, any answer POVM is a cross graining over the projector. That is a sub-measurement. The character is sub-measurement. And the states transform according to this Luder transformation rule. And with this result, comparing with the result of weak measurement, we find that G comes out to be lambda and F comes out to be 1 minus lambda square. It is another important point that the optimality condition is already with this in this formalism, because F square and G square equal to 1, it is straightforward. So, this measurement scheme is already optimal. Now, come back to the problem of shear beam non-locality. Here, Alice measures sharply in x or z direction spin, and first Bob measures in this direction unsharply with non-zero value of lambda. And final Bob 2 measures sharply, and the probability of Alice and second Bob is given by this, and the CHS expression for Alice and Bob 1 to root 2 lambda 1 and Alice Bob 2 is this. With this expression, there is a range of lambda for which they both get violation of del CHSS inequality. That means they both demonstrate non-locality. Now consider the three observer, Alice, Bob 1 and Bob 2. Here Bob 1, Bob 2 measures weakly and Bob 3 measures sharply. Then probability, joint probability, and finally one can calculate the CHSS expression for Alice and Bob 3, which is this denoted by I3. And in this scenario, Alice and Bob 2 obtain this, and Alice and Bob 1 obtain this, and Alice and Bob 2 obtain this. So it is a straightforward mathematical calculation which shows that these three simultaneously cannot be greater than 2. Any two of these can be greater than 2. When any two of these greater than 2, then the other will be less than 2. That means any two, Alice and Bob 1, Alice and Bob 2, can, if demonstrate non-locality, then Alice and Bob 3 cannot be demonstrate non-locality. Or if Alice and Bob 2, Bob 3 demonstrate non-locality, then Alice and Bob 1 cannot demonstrate non-locality. Hence the proof follows. Recently, there is a two experiment on this measurement scheme. One in September 7 appeared in archive. It is Italian group. This is Chinese group, and then Italian group in November they experiment and confirm there is no more than double violation. This is the measurement scheme done by Italian group. Here is the Alice measurement measures sharply, singlet state coming from source, and Bob 1 measures weakly. This box denotes the weak measurement scenario of Bob 1, and Bob 2 measures sharply. Here is the one particle of the singlet state comes to Bob 1. Here R is the unitary and it is the inverse of this operation, and it is coupled to another ancilla, and this measurement is denoted by this control phase gate, which is, and the epsilon is the amount of rotation given by this. The amount of rotation can control the strength of weakness of the measurement. So with this measurement scenario, they confirm that ICHSS 1, that is Alice and Bob 1 and Alice and Bob 2, can obtain this value of the CHSS expression. And within this experimental error, they confirm the violation of CHSS inequality.
Why is 2 the maximum? My question goes in the direction of Raphael Sorkin, generalized theories of quantum mechanics. Would you be able, if the world was ruled by one of those theories, would we be able to have a higher number of people finding non-locality?
Your question is why not more than 2 is obtained? What it is done here analytically, and it is obtained. If I go to beyond that, it is why this is happening. There is another condition that Bob 1 and Bob 2 all measures independently. That is, input of Bob 1 is unknown to Bob 2. If there is some information that what inputs is given to Bob 1 and what inputs given to Bob 2,